Hello everyone, this is Saksham and today I'll be talking about reinforcement learning for cutting plane selection in integer linear programming problems. The outline of the talk is as follows. First, we'll give a brief introduction to integer linear programming. Then we'll talk about the different techniques used for solving integer linear programming problems. Then we'll formulate a Markov decision process or a MDP for cutting plane selection. Then we'll give a vivid description of the deep reinforcement learning architecture. Then we'll talk about the experimental results which were obtained on employing deep reinforcement learning. And finally, we'll conclude. Moving on to the introduction. So integer linear programming problems are NP hard, and the prominent techniques used for solving integer linear programming problems are branch and bound, cutting plane, and branch and cut. Branch and cut is nothing but the combination of branch and bound in the cutting plane technique. But in our project, we'll be focusing on the cutting plane technique. And a pictorial representation of cutting plane technique has been depicted over here. Moving on to ILP formulation. So ILP problems in canonical forms can be written as like objective, we minimize C transpose X subject to the constraints AX less than equal to B, where X is greater than equal to 0 and X is integers. So X is nothing but a set of n decision variables. A is a matrix of rational numbers of size m cross n, which means there are m constraints and n decision variables, and B is a column vector of rational numbers of size n. Then XIP star basically denotes the optimal solution of the IP. ZIP star is the objective value corresponding to the optimal solution, which is nothing but the value obtained on substituting XIP star in C transpose X. Moving on to the cutting plane method for ILP. So the very first step, or you can say the step taken at the 0th iteration, we do a linear relaxation, which means we just drop the integrality constraints. So the feasible region of the linear programming problem at 0th iteration will be given by C0, X such that AX less than equal to B and X greater than equal to 0. We obtain the optimal solution for this LP at T equals to 0. Which is given by XLP star 0, and we can obtain the solution by using let's say simplex method. Now the objective value of LP0 is given by ZLP star 0. Now we know that the feasible region of ILP is contained in C0, so ZLP star 0 is less than equal to ZIP star, where ZIP star is the optimal solution corresponding to the IP, which is the original problem. Now we add a cutting plane to the feasible region C0. The equation for the cutting plane is A transpose X less than equal to beta. Now the feasible region will shrink to, let's say, C1, which will basically be a proper subset of C0. Now we'll obtain the optimal solution for LP at T equals to 1th iteration given by XLP star 1, again by using simplex method. And we'll keep on repeating this step until all the decision variables of XLP star are integers. Now let's talk about integrality gap closure. So after T iterations, the feasible region would have shrunk to CT. The integrality gap GT can be given as ZIP star minus ZLP star at Tth iteration, which will be greater than 0. Since the feasible region at T plus 1 will be a proper subset of feasible region at Tth iteration, we will have that the integrality gap at the Tth iteration will be greater than equal to the integrality gap at T plus 1th iteration, which means the integrality gap gets smaller and smaller with the number of iterations. Now the integrality gap closure after tau iterations can be given as the integrality gap at 0th iteration minus integrality gap at tauth iteration divided by integrality gap at 0th iteration. Now, this is a metric which we will be using for experimental analysis. Moving on to the Gomori's integer cuts. So after T iterations, let's say our feasible region is CT, the constraint matrix has transformed to A tilde. The constraint vector has become B tilde. IT is basically the set of components of XLP star T, I, that are fractional, which basically means all the decision variables which achieve fractional values on solving or will be contained in this set IT. Now for each component in IT, we generate a Gomori cut. And the set of all the candidate cuts, so basically the cuts obtained will be, all of them will be the candidate cuts. And these candidate cuts will be stored in DT. So basically DT is nothing but the set of all candidate cuts. And IT basically indicates the cardinality of this set DT. Moving on to the formulation of Markov decision process for cutting plane selection. So the first thing which comes into our mind when we talk about formulating an MDP is state space. So a state space is given by a set CT, which is the feasible region, C, which is the coefficient corresponding to objective row, XLP star T, which is basically the optimal solution of the LP at Tth iteration, and DT, which is basically the set of all candidate cuts at Tth iteration. Now, this CT is the feasible region, which is basically indicated by the set of these constraints, AI transpose X less than equal to BI, I going from 1 to NT. Now, NT indicates the total number of constraints, including the original linear constraints, which means all the original linear constraints which were given initially, plus the constraints which were considered as cuts up till this Tth iteration. Then moving on to the action space. So at Tth iteration, the available actions will be nothing but DT, which is basically the set of all candidate cuts at Tth iteration. And each action AT is basically an inequality EI transpose X less than equal to DI. Now the reward at Tth iteration is given by C transpose X LP star T plus 1 minus C transpose X LP star T, which is basically the difference of the objective function values at T plus 1th iteration and Tth iteration. Now let's talk about how the transition happens from state ST to state ST plus 1. So the state ST is given by this set. We take an action AT, which is given by an inequality. Now this inequality would have been contained in this set. After taking this action, the feasible region CT shrinks to the feasible region CT plus 1. C remains same because it's the coefficient of the in the objective row. XLP star T becomes XLP star T plus 1. DT becomes DT plus 1, which is basically the set of all candidate Gomori cuts at T plus 1th iteration, where CT plus 1 is given by CT union. So the initial feasible region union the new constraint which was taken as an action from state ST. Then moving on to the deep reinforcement learning architecture. So before talking about the granularities of this architecture, let's talk about the high level picture, what this architecture is trying to attain. So basically, we have a policy pi, which is parameterized by a parameter theta, and we want to find the probability of taking a cut, of making a cut when present in a particular state. So pi theta basically specifies the distribution over dp, which is nothing but the set of all candidate cuts at Tth iteration. So we are just trying to get the probabilities of what's the probability of making a particular cut in a when in the state ST. So for that we use an attention network. So because it is desirable that the architecture is agnostic to the ordering among the constraints both in CT and DT. So we just adopt ideas from the attention network from the Attention is All You Need paper by Vaswani et al. Here we have a parametric function f theta, which basically takes in a vector of size n plus 1 and produces a vector of size k, where k has been encoded in the network with parameter theta. Now, in the attention network, we have something called projections. So we have two projections over here, H and G. So H, the projections H basically denote the projections corresponding to the constraints, while projection G are the projections corresponding to the cuts. So HI, so for HI, we basically feed the constraint AI, comma BI. Now this basically has been concatenated. So this becomes AI is basically a vector of size n and BI is just an element. We concatenate it to make it a vector of size n plus 1. And we feed this vector of size n plus 1 to this parametric function f theta to get a vector of size k. And we do this projection for all the constraints. That's why I belongs to NT. Similarly, we feed this vector EJ, comma DJ. So EJ is basically a vector of size n, and DJ is just an element. So we concatenate it to make it a vector of size n plus 1. This vector of size n plus 1 is fed to the parametric function f theta, and GJ is basically nothing but a vector of size k. And this GJ is computed for all J's belong to IT, which means we compute GJ for all the cuts possible, for all the candidate cuts possible in that at the Tth iteration. Now we'll compute the score SJ for each candidate cut J belong to IT. So we pick the projection for a particular cut and take its dot product with all the projections of the constraints. We just sum it up and just divide it by the total number of constraints. And this is how we get the score for each candidate cut. After getting this score, we just take a softmax over this score to get the probability for each candidate cut. So once we get the probability for each candidate cut, so this is basically just the distribution over actions given by the policy pi theta in the state S. Then now in the previous network, we saw that we were forced to have an input vector of size n plus 1. Let's say if we don't have a vector of size n plus 1, which means we want to use the same policy network for instances with different number of decision variables. So in that case, we'll embed each constraint with the LSTM network, let's say LSTM theta. So for a general constant, AI tilde transpose x tilde less than equal to bi tilde, where AI tilde belongs to Rn, n tilde, where n tilde is not equal to n. So in that case, this vector AI tilde comma bi tilde is fed to the LSTM network. And in the nice thing about this LSTM network is the last hidden state of this LSTM network has basically n plus 1 neurons. So we just pick this last hidden state and use it in place of this concatenated vector AI tilde comma bi tilde in the attention network. So this is because the last hidden state was having n was basically a vector of size n plus 1. So this is how we resolved the issue when we wanted to use the same policy network for instances with different number of decision variables. Now we'll see the rollout of the policy algorithm. So what this algorithm is trying to do, it basically tells what is the reward obtained at each iteration. Or when you go from state S to ST plus 1, what is the reward obtained? So we'll take an input, the policy network parameter theta, an IP instance which has been parameterized by C, A, B, and the number of iterations, capital T. We initialize the iteration count as t equals to 0. We'll then initialize the minimization LP with the constraint C0, which is the feasible region at the 0th iteration, given by AX less than equal to B, and a cost vector C, which is nothing but the coefficient corresponding to the objective row. We solve this LP in the relaxed form to get XLP star 0 and generate a set of candidate Gomori cuts D0. Now we'll run a while loop. Now the condition for running this while loop has basically two conditions. The first one is, which we all know, that that if all the decision variables of the LP which was solved at dth iteration, if it was, or if all of the decision variables were not integral, then the loop has to go on. And the other condition which we added was to restrict the number of iterations, basically. So we put we restricted the number of iterations to be less than equal to capital T, because in ILPs of very large size, it might take a very long for this loop to come to a stop. So yeah, so we construct a state ST, which we described earlier. Then we sample an action using the distribution over candidate cuts given by the policy pi theta. We know the pi theta. And then here the action is AT, which basically corresponds to a cut. E transpose X less than equal to D, where which belongs to dt, where dt is basically nothing but the set of all candidate cuts at dth iteration. Now we append each cut to the constraint set ct plus 1 and shrink the feasible region. So ct plus 1 becomes a ct union and the action which was taken et e transpose x less than equal to d, and we solve for the LP problem at t plus 1th iteration, and then we generate the Gomori cuts at t plus 1th iteration. Then we compute the reward RT. Now RT is nothing but what we talked about earlier, is C transpose X LP star T plus 1 minus C transpose X LP star T. And then we increment T, and then this loop goes on. So this is how we roll out the policy algorithm, which basically computes the reward at each iteration. Then moving on to the training part of the RL network. Here we use evolutionary strategies. So it is nothing but a simplification of the RL problem into a black box optimization problem. So here the goal is to find the policy parameter theta that maximizes the expected reward J. So let's see what this algorithm is. So we'll take an input as the learning rate alpha. Then we'll take noise standard deviation sigma. We'll take initial parameter policy parameter theta 0, because policy has been parameterized with a parameter theta. So we have to take some initial policy parameter. So we take it as theta 0. Now we run these steps for a long period of time. That's why we have for t equals to 1, 2, up to so on. So the first thing we do is we sample some noise values, epsilon 1, epsilon 2, epsilon 3, and up to epsilon n from a multivariate Gaussian distribution, which has a mean vector of 0 and a covariance vector, which is basically identity matrix. Then for each noise value, epsilon I, we create a perturbed version of the policy parameter theta I dash equal to theta t plus sigma epsilon I. So we basically slightly perturb the current policy parameter using this epsilon. So theta 1 dash will be equals to theta t plus sigma epsilon 1. Theta 2 dash will be equal to theta t plus epsilon 2, and this, so we'll have up till theta n dash, which will be equal to theta t plus sigma epsilon n. Now we compute the expected return J under the policy pi, having parameter theta I dash, by just summing the rewards sigma k equals to 0 to t minus 1, rk gamma k from the trajectory of the policy pi theta I, where rk is the reward at the time step k of the trajectory and gamma is the discounted factor. So to clarify what rk is, so we have seen the reward at each time step. So this is basically rk. So, and we went from k equals to 0 to t minus 1. So you can see that in this algorithm, the number of iterations is less than equal to t. So basically, this is the t which they have talked about, t minus 1. And let's say if this loop stops earlier, which means this condition gets satisfied, then in that case, all the subsequent RK values will be basically 0. Then the next step in this training algorithm will be to compute GCAP, which is given by the expression GCAP is, so basically GCAP is nothing but the average value of J under this policy pi theta I dash multiplied by epsilon I by sigma. So we just take the average of this value uh, for all the noise values, epsilon 1, epsilon 2, epsilon 3, up to epsilon n. Once this GCAP is computed, we then update the parameter. So theta t plus 1 becomes theta t plus learning rate into GCAP. And this is how slowly we converge to the optimal theta value, which basically corresponds to which basically maximizes the expected return J. Then for testing the policy pi theta, which we obtained after training, so we test the performance of a trained policy pi theta by rolling out on a set of test instances and then measuring the integrality gap closure. So what integrality gap closure is, we talked about previously, which was given by G0 minus G tau upon G0. Moving on to the experimental results. So the experimental results were analyzed for three aspects. First is the efficiency of cuts, meaning how many cuts were required to reach to an optimal solution. So the lesser number of cuts, the better is the technique. And this basically analysis was done for very small sized IPs where they were able to reach the optimal solution in small number of cuts. Then the next aspect is integrality gap closed. So in cases where the cutting planes alone are unlikely to solve the problem to optimality, in that case, we see can the RL agent close the integrality gap effectively or not? Which means the higher the value of integrality gap closure will be, it means the closer we are to the optimal solution. Then the third aspect is we'll see how well our technique generalizes on size and structure. So we'll talk about it in subsequent slide. So the first experiment, so for small size IP instances, cutting plane was alone can potentially solve an IP problem to optimality. So we tested this, we did the experiment for 4 classes of IP. First is the packing problem, then is the production planning problem, then we have the binary packing problem, and then we have the max cut problem. And our technique RL was compared against 4 human design heuristic techniques. So one is random, meaning just randomly choosing a cut from the candidate cuts. The other one is max violation given by MV. Then we have MNV, which stands for max normalized violation. Then LE basically means lexicographical rule. And from the results, for all the 4 classes of problem, we can see that RL was requiring least number of cuts to reach to the optimal solution. So this shows that the RL agent was able to achieve close to several factors of improvement in the number of cuts required when compared to the baselines. Then moving on to when medium size and then moving on to IP instances of medium size and large size. So in this case, cutting plane I was unable to reach optimality alone. So we compared different cutting plane techniques with integrality gap closure metric. So for medium-sized IPs, we did 50 cuts, which means capital T is equal to 50. So to make more sense, the capital T over here has been substituted with 50 for medium-size IP instances. and capital T was substituted as 250 for large size IP instances. So now when we compare RL uh, with the four techniques for all the four classes of problem, we see that RL was able to achieve higher integrity gap closure values for all the four classes of problem for both medium-sized IP instances and also large-size IP instances. We can see the results over here that RL is performing better than all the four techniques. So this shows that on an average, RL agent was able to close a significantly higher fraction of gap compared to the other methods. Lastly, talking about how well the RL technique was able to generalize on size and structure. Now let's focus on the plots shown on the right. So basically the x-axis denotes the percentile of IP instances which were solved, and the y-axis denotes the integrity gap closure. Now focusing on this green and blue curve. So let's say we have, and for a packing problem, IP instance, there's an IP instance of size X. So the RL agent denoted by green. So RL by 10X agent was basically trained on IP instances of size X by 10. And the curve shown by blue is basically the RL agent which was trained on IP instance of size X. Although the RL agent, RL by 10X agent, which was trained on a smaller, on 10 times smaller IP instances, yet we can see its performance in context with the integrity gap closure was very competitive to the RL agent, which was trained on 10 times larger size IP instance. So be it a packing problem, be it planning, be it binary packing, be it max cut, we can all the four plots show that the RL agent, which was trained on 10 times smaller instance than the test instance, was showing very competitive performance. Now let's shift our focus to the plot on the left. So here, the green plot basically shows the RL agent, which was trained on for a packing problem with IP instance of size, let's say X, and the blue curve was basically trained on max cut problem of size 10X. So which means the RL agent shown by green curve was trained on a different problem as well as on 10 times smaller IP instance. But still, it was able to show a very comparable performance to the RL agent, which was trained on the same problem and 10 times larger IP instance. This shows that the RL agent uh, generalized well for size as well as structure, which means if trained on a particular class of problem, it will generalize well with when tested against a different class of problem. Moving on to the conclusion. So we presented a deep reinforcement learning approach to automatically learn an effective cutting plane strategy for solving IP instances. The RL algorithm learns by trying to solve a pool of randomly generated training instances again and again without having access to any solved instances. And the RL agent learned an intelligent algorithm for selecting cutting planes, as it was able to generalize on a variety of tasks without being trained on it. Moving on to the references. So this is the paper which I just presented. And thank you so much for listening.